Good morning. Welcome to the fifth lecture of this course on advanced computer algebra. After having completed the first part, which consisted of a discussion of fast multiplication and fast division, we're now turning to algorithms that take advantage of fast arithmetic, as discussed in the first part. And I want to show you some examples to illustrate that algorithms do not automatically get faster if you just replace a usual multiplication algorithm by a fast multiplication algorithm. Instead, you usually have to modify the algorithms a little bit so that the efficiency of fast multiplication translates into also a better efficiency of the other algorithm in which you use multiplication. Okay, so the first example for such an operation is evaluation and interpolation. Is a very important technique in computer algebra that you use all over the place. We already used it as a design principle in the FFT-based multiplication algorithm. You remember that this was based on the observation that the values of the product are the product of the values of some polynomials, and then the FFT algorithm did the evaluation and the interpolation fast for a specific choice of numbers. Now, evaluation and interpolation is more important than just for this application. You can use it in many other applications, and not only in the design of algorithms, but also as a user of computer algebra. And that's what I want to discuss today. I want to recall what you probably have heard in Computer Algebra 1 already or in other courses, why evaluation and interpolation is important and what it is used for. So today I will explain that a little bit informally and without focus on how to do that efficiently. I will just explain why is that an interesting and important technique. And next time, then I'll show you how to do this quickly, and we'll discuss how quickly we can do this. So evaluation and interpolation. Here's the thing. The problem is that numbers get bigger when you compute with them. If you think of rational numbers with a numerator and a denominator, let's say they have all these numbers have 10 digits. Then the result of an addition or a multiplication is a fraction where the numerator and the denominator will have 20 digits in general. So the number of digits doubles with every arithmetic operation, and that's painful, because you can imagine if you do a few operations, then you're not going to get very far if the size of the numbers doubles in every step. So that's something that we have to worry about. And the typical situation is, so you might expect that this is just what it is and there's nothing we can do about it, but it's not quite true, because typically you are faced with a situation where the input has small numbers. Well, small compared to what? Well, let's just define that the size of the input is what we consider small. And then the output is also small. Often, not necessarily, but often the output is small compared to the things that you see in the middle of the computation. The intermediate results that you obtain, the numbers that you see on the way going from the input to the output, can be much bigger than both the input and the output. And you don't care about these numbers. You're not interested in them. You just somehow, the only reason why you compute them is because you want to get to the output. So why is the output smaller than the intermediate expression? Well, there's no mathematical reason for this, in general at least, and it's also not necessarily always the case. But if you accept a philosophic argument, then the reason could be that you're not interested in solving random problems. You want to solve problems that come from somewhere, from some application that have some meaning. So for these meaningful problems, the output also has a meaning. So it's a reasonable expression, and therefore you can somehow expect that it has a reasonable size. Unlike the intermediate expressions, they have somehow much less specific meaning, and therefore they have much less reason to be well behaved. And that agrees with what we observe in actual computations, that they do not behave. These intermediate expressions can be much larger than both the input and the output. So let's look at this for a concrete example. Let's do an experiment and compute the null space of a matrix. So that's just an example for some problem, and you could consider any other problem instead. But let's choose this as an example for today. We want to compute the row-reduced form of a matrix with 100 rows and 120 columns, so that the null space is probably a vector space of dimension 20. And we want to use Gaussian elimination. Okay, so I've chosen a random matrix with entries that are numbers between 1 and 9, so 1 digit. And I've measured how the size of the matrix changes during the execution of Gaussian elimination. Now, of course, the size of the matrix doesn't really change. It will always have 100 rows and 120 columns. What I mean by size here is the total bit size. That means the size that the matrix occupies in the memory of the computer. And that involves not only the format of the matrix, but also the size of the entries, the number of digits that the entries have. Okay, and here is what it looks like. If you do the Gaussian elimination over Q, then then you start with something small here, and then it very quickly goes up, and here you're for some reason fortunate that it doesn't continue with that speed to grow, but then it continues to grow here, and then here it does something irregular, and then from some point on the size gets smaller again until here you have the final output. And I remember what I said, the output is typically much smaller than the intermediate expression. So and here on the horizontal axis we have the row operations. So after 2000 row operations we have a matrix that is that big. So it's a small example, it's just in the range of megabytes, but you can imagine that if I choose a bigger example, this steep portion of this journey here will get more and more more and more painful. So it can well be that in another example you have something where you can't even draw it. It starts with something here and then it goes out of the picture, and in the end it drops to something reasonable. And if this here is beyond the limits of your memory, then you are really in trouble. Okay, so this is if you do the computation in Q, and here's the same picture, just illustrated in a different way. I've shown here the matrix. This picture shows the matrix. The matrix is here represented as a rectangle, and you can think of every pixel representing an entry of the matrix, and the color represents the size of the entry, the number of digits, or the bit size. So blue is cold, that means it's just a small matrix, a low number of digits. And then as we continue with as we initiate Gaussian elimination, you see that this goes very quickly in the beginning, but then it starts to slow down. And the entries here start to get bigger, as indicated by this color. It gets bigger, gets bigger, gets bigger, and as it gets bigger, it gets slower and slower and slower. And so you just have to wait until this is finished. Eventually, it will finish. And here you see this is extremely big. This is the steep point in the red curve. But then in the back substitution phase, it goes very smoothly, and this big stuff is getting replaced by green stuff. Green is worse than blue, but not as bad as red. So this is how it goes. I can show you another illustration. So here is an experiment with Mathematica. I have prepared a linear system which has certain dimensions. So let's see how big. So it's not exactly the system from this experiment. It's a different one, but of course they all behave similarly. So maybe we can look at it. No, we cannot look at it because it's too big. So it has, you see, it has rational numbers, and it also has a symbolic parameter x in it to make it more funny. And let's see what it takes. I can see what is the degree exponent. This is x max. So there's polynomials of degree 50. It's not so big. Right count. You can also see. So this is a matrix that has 30 megabytes in the original size. But now let's see how long it takes to compute the null space. So timing null space is this, and maybe we don't want to see the null space. Let's just assign it to something, and the semicolon makes sure that we don't get it printed out because it might be big. So I'm choosing the out-of-the-box null space method that comes with Mathematica. Yeah, there's no point in waiting here, so let's put this on the side and come back to it later. What can we do? Well, you know the answer. The problem here is not the Gaussian elimination. The problem is that we are not computing in the right domain. We are computing in Q, and we shouldn't be computing in Q. If we instead compute in a finite field, then this is what it looks like. In a finite field, there is no growth of the coefficients, so the matrix stays the same size from the beginning to the end. And this translates into a very, very favorable runtime. So here's what it looks like if you solve the problem, if you solve the matrix not over Q, as we have seen in the first video, but over Z. That's it. So you want to see it again? Tack, tack. This is much faster than the computation that we saw over Q. It's the same number of operations, by the way, because that's just determined by the size of the matrix, the format of the matrix. The first one took longer because it had longer entries. So that's something that we have to worry about in order to make this fast. Okay, and the idea for doing this is to use homomorphic images. Homomorphic images is what I recalled already at the beginning of the video that we used in also in the design of the fast multiplication algorithm, where we said that the product of the values is the value of the product. And more generally, this means that if you the magic of a homomorphism is that you can solve a problem in homomorphic images, and you have that the image of the answer is the answer of the image. The setting is then if you have an integer and you want to compute some function, for example the null space or whatever you like, some function where the result is again an integer, then maybe this is a hard problem and you can't do that directly, and the solution is you do this in a homomorphic image. So you take the equivalence class mod p for some prime, and then it's easy, that's the assumption here in this general picture, it's easy to compute the image of the answer in this finite field. So in order to connect the two, you have to go from the x that is the input to your problem to its modular image. That's easy. You just take x mod p, and then you have a nice representative of this equivalence class. But then you also have to go back, and that's more, that's less obvious how to do this, because this f of x is not uniquely determined by its equivalence class. So you have to worry about how to get from the equivalence class back to the actual answer of the problem that you want to solve. Okay, so how do you do this? Let's say we take a prime, fixed prime p, and we consider the function that maps the prime, that maps any integer to its equivalence class modulo the prime. So this is would look like this. Here is the integers written down, and the x that I'm interested in is some point on this, some point in the integers, maybe here. And then if you go to the equivalence class, then you know that the equivalence class contains all integers whose distance to x is a multiple of p. So maybe these are these red points here. And then an equivalence class is typically represented by the point that is closest to the origin. So that's here the green triangle. And if the x is the output of a computation, then you don't know which of the red points is really the output. You know just one of them is the real output. So possibly it's not the one that you use to express the equivalence class, because that's the green one. It might be this one. And you somehow have to do something to make the green and the blue one match. Because when that happens, then you know that the one that you have in your hands is actually the one that you're after, that you want to have. So you know that because the distance of any two red points is p, you know that there's at most, that there's exactly one point in this yellow region, the yellow region which extends from minus p half to plus p half. And this means that if you make the p large enough, there will be only one here, there will be only one possibility. And if it's so large that it includes the blue one, then the blue one must agree with the green one, because there's only one, and the green one is always the one that is in the yellow part. But if the blue one is also in the yellow part, then because of the uniqueness, the green one and the blue one must agree, and then you know that you're done. And then you know that you have really your answer in the integers and not just in the finite field. Okay, so how can we make sure that the yellow part is big enough in this sense? There are two possibilities. The first possibility is that you know in advance how big the answer could possibly be. You maybe have some bound, some theoretical bound, because you understand the problem that you are solving well enough, that you can tell the integer that I'm looking for has absolute value at most m. If that's the case, well, then your solution could be you choose a prime that is bigger. So big that you know that you are in a situation that is shown here. So big enough would in this case mean it should be bigger than 2m, because you go from minus p half to p half. So you don't know, if you don't know whether that, so if the x can be positive or negative, then you have to do 2p. If you know that it's positive, then actually p is enough, because then you can cut the you can move the yellow bar so that it starts at 0 and extends to p instead of going from minus p half to p half. Anyway, but let's consider this situation. The other is completely analogous, and that's one possibility. But there's another possibility. Maybe you don't have such an m, or maybe you have an m, but the m is pessimistic. Maybe it's bigger than necessary, and you don't want to make the prime bigger than necessary, because it also costs computation time. So you look for another possibility, and here is another option. But it's again an assumption. Maybe you can check efficiently whether you are done. So if you have for a given green triangle a possibility to efficiently check whether this is actually the integer solution of your problem, so whether the xi is equal to the x, then you don't need to worry so much about the choice of the p. You just choose some p and then you check. And if it doesn't work, you try again with a larger p. Maybe you double the size of p, and you keep increasing the size of p until eventually the yellow area is big enough, and then you know that you are done because you will recognize it when the green triangle agrees with the blue triangle, because in this scenario the assumption is that you can do this. These are the two possibilities. But this is if you are in the integers. Now, what if you are in the rational numbers? Then you can proceed roughly in the same way, but there's an additional complication. It's the denominators. So situation is the same as before. You assume you have a function f that turns rational numbers into rational numbers, and it's hard to compute because rational numbers are difficult, and your idea is to go over a finite field. So you can go mod p. That's easy. You know how to do this. You take the modular inverse of the b and multiply it by a, and the modular inverse of b, you remember this is from the extended Euclidean algorithm. You know that b and p are coprime. Hopefully they are. If they are not, the b here at this point is any integer, so it could contain p as a factor, but if it does, then you should better choose a different prime, and p is not a good choice. So if p is not contained in p, if p is not contained in b, then these are co-prime because p is a prime. And so you can write, so the GCD is 1, and you can always write the GCD as a linear combination of the inputs. So there are S and T such that 1 is equal to SB plus TP. And now if you take this equation here, mod P, then this goes away, and you find that the X here is A, the numerator, times S, this cofactor, as equivalence class mod P. So this is going down. Already a little bit more complicated than in the case of integers. Now you assume you can easily solve the problem in the finite field. And now again you have the problem, how do you get back? So if you have your answer mod p, then how do you get back u and v, the numerator and the denominator of the answer of the original problem over q? You can do it essentially in the same way. So here we have again the setting of some function that turns x into its equivalence class. Now that's not really a function because, as I discussed before, the b could contain the p. In that case we would say the p is an unlucky prime, but the b, whatever the b is, it contains only finitely many primes, so there are almost all primes are not contained in b, and I'm choosing one of them. I don't know in advance perhaps which p's can occur in the denominator, but I don't need to know this in advance. I just try a p, and if it's a bad p, then I will realize this, because during the computation in the finite field I will run into a division by 0. Okay, this is bad, but it's better than getting a wrong result. So if I run into a division by 0, then I know I haven't chosen the right prime, I was unlucky. And I choose a different prime, I try again, and it's very, it happens that you run into an unlucky prime. It's not a situation that occurs with negligible probability, but it's not something that occurs so often that we have to worry about how to avoid it. We just try it, and maybe from time to time, like once a year or so, I hit an unlucky prime, and then I start again with a different one. Usually the first prime that you choose will be okay. Of course not if your prime is 2 or 3 or 5, but you choose longer primes, and we will discuss later today how you choose them. Okay, so here's the picture in the rational case. The rational case is a two-dimensional extension of the picture that we had before. There's again a triangle that points to some point in the plane that represents the numerator and the denominator. So let's say the numerator is depicted here horizontally and the denominator is vertically. So I need the sign I attach the sign to the numerator, so the numerator can be positive or negative, and the denominator, I don't have to assume that it's negative. I can switch the sign always to the numerator if I like. So this is then a picture that shows me all the rational numbers. And now if this is the number that I want to reconstruct from its homomorphic image, then let's see what the equivalence class looks like. The equivalence class now not only contains integers, but it contains all rational numbers that are equivalent to x mod p, and they are arranged in such a grid. And the number that we use to represent an equivalence class is typically an integer. So it's something that is down here close to the axis, not exactly on the axis because that would be 0 denominator, but it's just one level above the axis. Okay, that's the one that we compute. We compute with integer representatives of this equivalence class. But if I want to recover from the equivalence class a candidate for what the rational number was that produced this equivalence class, then I cannot restrict to integers because then I will never hit this point. So instead of choosing an integer that represents this class, I choose the red point that is closest to the origin. Okay, so maybe this one. No, not maybe. This one. And then there's again the same story as before with the yellow picture, or with the yellow box. In this case, it's a two-dimensional box, and you can show that in this box, where I'm telling you later what its dimensions are, there is exactly one red point. And so, if you want the green and the blue triangles to match, one way is to ensure that the yellow box is big enough. So let's make the yellow box bigger and see how the choice of bigger primes, so the size of the box is determined by the size of the prime. So in order to make the box bigger, I have to make the prime bigger. But if I choose a different prime, I get completely different red points. So here's what this looks like. They jump around these red points, except this one. This one will stay because that's the right one. And this one will also stay. Well, what is this? Well, that's actually the same number as this. Just here I have reduced the fractions. Here this is the point where numerator and denominator are co-prime. And here I get to this point from here by multiplying numerator and denominator by 2. And then here's another point. It's not shown anymore. That's where I multiplied by 3 and so on. So this one will not go away. But all the others are somehow pressed out of the area. And you've seen also in the animation that the green and the red one already match even before the box has reached a size where it includes the target. Okay, so this works again. And the conclusion is for sufficiently large prime, I can be sure that the green and the blue triangle match. And the question is again, what is sufficiently large? And the answer is again that there are two scenarios. And they are the same scenarios as before. Maybe you know a bound on how big the numerator and the denominator can become. So maybe there is a bound on the sum of the absolute values of numerator and denominator. And in this case, well, here's some of the information on how big the box is. You have to choose a prime that is more than twice as much as m squared. And then you can be sure that u and v can be uniquely determined from the psi that is defined as the fraction that is equivalent to x and has the smallest numerator and denominator. The other possibility is you can check efficiently whether you are done, and then you just keep increasing the primes until you match. Okay? Good. So that's nice if I draw this in pictures, but how do you really do this? That's not really an obvious thing to do. If I look here at this animation, I'm drawing where all these points are, but how do I really know if I have given an equivalence class what is the numerator and the denominator of the green arrow? That's something we have to discuss next. So the question is, given an x and a p, and I'm thinking of x as as an integer representative of the equivalence class mod p, how can we find a numerator and the denominator where u such that u over v is equivalent to x mod p? The answer is the Euclidean algorithm. The Euclidean algorithm knows this because if you think of this equation, you prepare it a bit, move the v to the other side like this, and then expand also the definition of this mod p, which just says that this is equal up to a multiple of p, then you see this really looks like in the extended Euclidean algorithm. If you apply the extended Euclidean algorithm to x and p, then in the course of the algorithm you will have a loop invariant that says that if you start with this as the candidate for the GCD, and then eventually after the execution of the algorithm this will be the GCD, and here you have the cofactors v and w, and you have such cofactors not only at the end of the Euclidean algorithm, if you remember how this works, but you have it throughout the algorithm. So you start by maybe p is equal to 0 times x plus 1 times p, and x is equal to 1 times x plus 0 times p. This is the initialization of the extended Euclidean algorithm, and then you keep running, and then it looks a bit like this. Here's the prime as an example, and an image representative of the equivalence class, and you see v and w are very small, and I've printed the w here in gray because we are not really interested in the w. We want to take this here mod p, so this will go away anyway, so let's not worry about this column. Let's focus on this column. And on this column, here in this column you see what happens, that it proceeds as you expect. You start with something big, and as you work through the Euclidean algorithm, you make this smaller and smaller. You're taking consecutive remainders. You're taking the third row is the remainder of the division of the first row by the second row, and every row here is the remainder of the division of the first of the two rows above it. So it's clear that this gets smaller and smaller, and it's also actually clear that the result is 1, because x is now, unless x is 0, okay, in this case it's not so interesting, but if x is non-zero, then you know that the GCD of those two is 1, and so there's actually no reason to compute it. The reason why we are computing it is because we are interested not in the final result. So this here would be the modular inverse of x mod p, but that's also not what we want. We want to look at the intermediate things. So you see that this here is getting smaller and this is getting larger, and it's in terms of the number of digits, it's roughly linear. So here I could draw a line here roughly, and here I could also draw a line, but if you focus not on the length of the numbers but on the value of the numbers, then you see additional digits make really a much bigger difference. So this number here is not just 1 digit longer than this number, it's actually more than twice as long, or twice as big as a number than this one. And in the other direction also, this one is maybe 3 times as big as this one in absolute value. And here the factor is even 27, and here it's 2, and here's much. Okay, so there's one row where the sizes of the two entries in the two rows are somehow balanced. And that's this green row. Here you see this number is roughly as big as this number, in the sense that if you take the sum of the absolute values of the two numbers, then it is minimized here. Because if you take the sum here, then this is so much bigger than this, that the difference between this and this is not enough to balance this out. And here in the other direction, here now this one is so big, so much bigger than this one, that this is not enough smaller than this, that the sum of this would beat the sum of this. So this is what you can choose. So every pair of numbers here is a red point in this picture that I've shown on the previous slide. But this one here that appears in the Euclidean algorithm is the one that is closest to the origin. Now, this is not I've not proven anything here, and I'm not going to prove it here. I hope you've done this in Computer Algebra 1, and if you haven't, then you can look it up in the book of von Sorgaten and Gerhardt. But it's not the point today. The point today is not how or why this works, but the question is how it works, and more importantly, even why we do this. Okay, and I've motivated why we do it because we want to compute the solution of our problem in a finite field, and then we have to go back to the rationals if the original problem was formulated in the rationals. Okay, this is the first part of the story. And now about the second part of the story. You should see that in the second scenario, we are throwing away a lot of information. So we are trying a prime, we are solving the problem modulo this prime, and then we realize the prime was too small because green and blue do not match yet. So we throw away the result that we computed and try another prime. Well, that's not going to be efficient. We will waste a lot of time in computing outcome that is too small, that turned out to be too small, and then we have to compute with a bigger prime to start from scratch. That's not what we should do. We should be more, we should recycle information that we have computed. And the question is now how to do this. So after a computation modulo m that the thing that you're looking for is in this equivalence class of x mod m. So that means you know the red points in this equivalence class. Then if you compute it for another prime, then the result also looks like this, but it looks different. So here we get a different green triangle from before, and also they are differently spaced. The red points are differently spaced because n is different from n. But I know that the x that I'm looking for is in both. So it's here and here. And I can use this because I have this information and I have this information. And if I could somehow intersect these equivalence classes, then I would know, well, the blue triangle must be here. And you see in the picture that the combination of the two equivalence classes here, the two computational results that are shown here, contains much more information than if I just choose yet another prime of approximately the same size as before. It would be again an area like this, and if I choose a slightly bigger one, then the area would be slightly bigger, but here the area gets much bigger in one stroke. So this is the Chinese remaindering theorem that says how you can computationally do this. So it says that you can given any representative of this class and any representative of this class, you can compute a representative of the intersection, and the intersection is always also an equivalence class where the modulus is the LCM of the two moduli of the classes that you're intersecting. So in the case when n and m are primes, the LCM is of course the product. So this is an illustration of this. Here is a number sequence that I took from some application in combinatorics. So this counts how many, I don't know what it was, maybe how many graphs or how many trees or how many walks in a lattice or how many whatever combinatorial structures there are if I have a size. So there's a parameter that says, think of maybe graphs with a certain property and so many nodes. Then there's no with one node, and there are so many with one node and so many with two nodes and so on. And you see that this grows very quickly. And maybe you don't want to compute this sequence over the integers because integers get longer and maybe that's too costly. So you can compute them modulo prime, and then you get the modular images of this prime. You see nothing changes as long as the numbers are smaller than this modulus, but here it somehow gets wrapped around, and then you get garbage. Well, it's not really garbage, it's just we don't see the information anymore with the eyes, but it's still there. And then if you compute this with another modulus, you get something that looks similar, and similar, and similar, and similar. And then you can merge this information. So in a sense, computing modulo a prime is again a form of approximation. It's not an approximation in the way how you do it in numerical analysis, where you say something is close if it's close in the Euclidean distance. That's not the point here. The point here is that it's an approximation in the sense that it contains some of the information. And this also contains some of the information. Another way of viewing it is that you can think of the modular images as shadows. If you have an object in a three-dimensional space and you shed light on it, then it throws a shadow, and the shadow gives you some information about the shape of the object, but not the complete information. If you put the light in a different direction, you get a different shadow, and maybe from the two shadows combined, you can get more information about the shape of the objects. And if you have sufficiently many shadows, then you can reconstruct the shape of the objects entirely. And that's what the Chinese remaindering theorem does. It says I can combine these two approximations, each of which has a certain accuracy. It's given by the number of digits of the prime, and I can merge them to approximation which is twice as long, so which is as long as the two lengths of the given approximations combined. And then you can keep doing this and keep doing this, and then you have reconstructed the original data that was data over the integers. Now it's still modular data, strictly speaking, but the modulus is so big that you cannot recover the green, and you cannot distinguish the green triangles from the blue triangles, so you can as well read these numbers as integers again. Okay, so this is the Chinese remainder algorithm. Let's briefly have a look how this worked computationally. So we had four numbers as input. Two numbers were the moduli, and two numbers were representatives of the equivalence classes. And yeah, to make it simple, let's assume that the moduli have are coprime. And the task is to compute a U which is equal to one of the images modulo one of the primes. It doesn't have to be a prime here, but let's say they are primes, and it's equal to the other. This is a typo. This should be UQ. It's equal to the other image modulo the other prime. Okay. And the key is again the Euclidean algorithm. The extended Euclidean algorithm tells you that since P and Q are coprime, you can write 1, their GCD, as a linear combination, or this is another typo here, this should be P and Q, as S times P plus T times Q. And so this means if you take TQ times UP, and SP, here is correct, times UQ, and you see what happens if you take this mod P. If you take this mod p, then this one will disappear, and this one is equal to 1 mod p, because this one disappears. Remember, this is a p. If I take this equation mod p, then I see tq is equal to 1. So mod p, this is equal to 1. That means if you take this here, mod p, you get up as you want it. And this is a metric, so it works the other way, the other direction in the same way. If you take this expression mod q, then this one will drop out because there's an explicit factor q. And this here is 1, this product sp, because if you take this equation mod q, then this one will disappear. And remember, this is sp, so sp is equal to 1. And that means this here disappears also, it becomes a 1. This becomes a 0, so this drops out completely, and I'm left with uq. So this is really an integer. It's really an integer which has these desired properties, that it's mod p equal to this, and mod q is equal to this. Okay, so this is what I can take as u. If you have several images and several primes, then and you assume that the primes are, or the numbers for that matter, are pairwise coprime, then you can repeat this step by step. And do this calculation that we did here, just one after the other, to get an integer that is equal to ui mod pi for every I. So here's how you do it. You initialize this with the first image. That will be valid for the first modulo, the first prime. And then here you take an m that will contain the product of all the primes, and then you run over as many points as you have. And here you update the product. Here you take the modular inverse of the product modulo the next prime, call it s. And here this formula is a slightly more efficient than this one, because this expression that I had here is useful for showing what is happening, but it's not the one that we want to use in computation, because this will be in general larger than p times q, and you want to have something that is smaller than p times q, because you want to have the canonical representative of the equivalence class mod p times q. So here is the same formula, just slightly optimized. You take uk, the new image that you want to accommodate, minus u times the modular inverse s. Then this is an integer. You take it mod pk and multiply it by m. Now we can check also here that this makes complete sense. So you prove the correctness of this by induction, and by induction the value of u before this assignment will be such that it matches all the values of u's, all the homomorphic images up to the k minus first, and this update should turn it into an integer that also matches the kth. So there are two things to check. First, whether you don't destroy the properties that you already had, and secondly, that it has the property, the additional property that it is supposed to gain in this step. And for the first thing to check, you see that this m here is the product of all the primes that were considered so far. So if you take the new m, whatever this is, and take it mod pi, then this one will be 0, so this doesn't matter, and the result will be u. So the new u and the old u will have the same image mod pi for every I that is less than k. That's the first thing. And the second thing is, what about k itself? If you take this mod k, then the s has been chosen so that it's the modular inverse of m mod pk. So this means that this s and this m cancel each other, and what remains here is just uk minus u. So this u cancels with this u, and all that is left is the uk, or possibly up to a multiple of pk, but that's okay because we want to get that only mod pk. So it's really easy to see that this is correct. Okay, what are the features of this algorithm? One feature that I already mentioned and used as a motivation for this is that you're not wasting computation time if you're in the scenario 2, where you don't know in advance how big your prime should be, and you just keep going and increasing the size of the prime until you hit the result that you're looking for. But there's another feature. The other feature is that you can do several primes at the same time and solve the problem simultaneously, possibly on different computers or on a computer that has several processors, and get several homomorphic images computed at the same time. So in this case, in this way, you can save speed by parallelization. Parallel algorithms can be more complicated if the parallel processes have to communicate with each other, but that's not the case here. You're just distributing primes on the different processors, and then each processor just has to solve the problem modulo its prime and doesn't have to communicate with the other processes. Eventually it has the result, and then you have all the results, and then you do the Chinese remaindering. But the Chinese remaindering is cheap compared usually it's cheap compared to the problem solving, so it's enough to parallelize the problem solving. You don't also have to parallelize the Chinese remaindering. And another point is that even in the scenario 1, where you know in advance how big your prime should be, it's not always a good idea to use such a big prime, unless the prime that you need is not very big. But imagine that this capital M, this bound that I showed you there in this scenario, or that is assumed there to be known, imagine that this is very big, then you would have to compute with a very big prime, and you don't want to do this. Why not? This has technical reasons. So there's no theoretical advantage no, there's no significant theoretical difference between computing modulo 10 primes of a certain size or modulo 1 prime of 10 times the size. So that's roughly the same in theory, but not in practice. And that has to do with the way computers work. So in order to get an idea of what the optimal choice of the size of a prime is, if we compute on a real computer, let's do some more experiments and see what is the cost of integer multiplication on an actual computer for an actual software, depending on the size of the integers. So here's an experiment that I did for you for 3 software systems, Sage, Maple, and Mathematica. And you see this is microseconds, and this is the bit size of the primes. And you see, okay, there's something funny going on here. Probably it's a bug, but otherwise they all agree that there's actually not very much growth in the size of the integers, in the size of in the computation time. Depending on the size of the integers, it grows a little bit, but and it grows more considerably if you go to even larger numbers. But what we observe here is really the effect of fast multiplication. So the fast multiplication says that if you have integers that are twice as long, then you essentially need twice as much time to multiply them. Oh, okay, but that means if it's really like this, then there's no then it really doesn't make a difference what size of prime we choose, because if we choose 2 primes, and then we also have to do twice the work of a single prime. But if we chose a prime that is twice as long, we also have to do twice the work of a single prime. So that it seems that this doesn't give us any clue which size of P is the best. There's another experiment where we see more, and in the other experiment we go not so deeply into the arithmetic. Here I'm just taking the time of a single multiplication. But you're not just doing a single multiplication and then you are done. You're trying to solve a more complicated problem, problem that involves several steps and possibly not just multiplication, maybe also memory allocation and I don't know what else. So let's let's do the same experiment, take some timings, but with respect to a more complicated operation, and let's take again a null space computation. So here's the timing that I observed, that I measured for computing the null space of a matrix, 300 times 301, for various choices of p. And here you see the effect that I wanted to show you. Here is the bit size in this direction, and here's the computation time. And you see that there's absolutely no computation time needed, well, almost absolutely no computation time needed, up to a certain point. And where this point is, that depends a bit on the software. So blue, I forgot what blue is. Blue is maple. Blue has the jump at 32 bits on my computer with my version of maple, which is perhaps not the most recent one. And Mathematica has the jump at that seems to be 63 bits, and then it jumps actually higher than it should jump, and then it continues here. And then Sage goes in 2 steps. But what the point is of this extreme growth, or first, what is the reason? The reason is that in a computer processor, on the chip of the computer, there is a hardware, hardwired hardware that does multiplication for small numbers up to a certain size. So a computer can compute the product of 2 numbers in 1 step as long as the numbers are not too big. And computer algebra software can work with numbers that are arbitrarily big, but if they are bigger than what fits into a single processor instruction, then you have to do a software multiplication, and that then looks a bit like the algorithms for polynomial multiplication that we have discussed earlier. But what we have here, what we see here is exactly the transition between the hardware multiplication, which is extremely fast, and at some point, at some size here, it switches to software multiplication. And software multiplication is much slower. So if you have a choice which primes you want to use, you want to choose primes that are just before this wall. So in Mathematica, you choose a prime of this size. You want to choose not smaller than necessary, because that would mean you need more primes. You don't want to use more primes than necessary. That's why you want to choose big primes. But also you want primes to be smaller than this jump, because after this jump you have to pay much more for a single instruction. So this is why you choose primes that are just below whatever your software tells you what the jump is. Okay. So typically it's 32 or 64 bits on primes that work just below because this is how our computers are built. It has no mathematical reason, it really just has a technical reason. Okay, so this concludes the discussion of Chinese remaindering. And it also concludes the discussion of how I would compute the null space of an integer matrix if the integers are long in the matrix and the solution is perhaps not as long as it could be in the worst case. I will compute it modulo prime for several primes and then use Chinese remaindering and rational reconstruction to to translate the modular images back to an integer answer. Okay, now the next step is to go to polynomials. So if you have rational rational functions instead of rational numbers over a certain field, well then essentially you have the same problem, that addition and multiplication doubles the size of the elements. The size in this case is the degrees of numerators and denominators. And that means, like before, that you can't get very far just by computation. By just doing arithmetic in rational function fields. Sometimes there's no way to avoid it, but usually there is a way to avoid it, and it's the same as before. It's the same solution as before. You take modular images, so you take the rational function field and you translate it to quotient rings in the possibly several ones. In the quotient rings, you can easily solve the problems. You get solutions in the quotient rings. Then you do Chinese remaindering to merge these answers into an answer that is valid modulo the product of these moduli that you've chosen. And then you do Chinese remaindering, and then you do rational reconstruction to turn this modular image into a rational function. Okay, and the question is again, like before, how do you choose these p's? For the integers, we have seen that we choose the p's in accordance with the size of, in accordance with the hardware on which we are computing. Here there's also a preferred choice, and that's to choose polynomials of degree 1. This has an advantage. The advantage is that if you choose here a polynomial of degree 1, then kx mod x minus something, that's really just isomorphic to k. So you have really eliminated the x from the computation. And here, in this part, there's no x anymore in the business. You're just computing in k. Okay, so this is fortunate, because the x is something that could cause slowdown. So if you can get rid of it completely, then that's a good option. In principle, you could choose something different. You could choose here something of higher degree, but it's not giving you any advantage to do so. It means you can get along with fewer homomorphic images, but each of these images will be twice or 3 times or 4 times as expensive as this choice, so you're not gaining anything. On the contrary, it's getting worse, because there's still the x floating around and you have to do polynomial arithmetic, whereas here you just have to do arithmetic in k, and depending on what k is, this may be much more efficient. Okay, so in this case, for this choice, the Chinese remainder theorem requires that the two pi's are co-prime, and that means, translated to this setting, that the evaluation points, which I've named Z here and A here, sorry for this, should be different. And the modular image of a polynomial or a rational function modulo such a polynomial pi is just the value of, there's another typo, this is f of ai, and here I'm back to a, I'm sorry, it's just the value of the polynomial at this root of p. So mod is evaluation. I'm sure you have seen that before. And so Chinese remaindering is the same as polynomial interpolation. Okay. And what is the cost of evaluation and interpolation? That's a question I didn't want to discuss today. That's a question I prefer to do next time. So far we have not talked about how we solve these problems, the problem of evaluation and interpolation. The problem is, not the problem is, there are algorithms that you discussed hopefully in computer algebra 1, like the Newton interpolation algorithm, and also the evaluation algorithm, the polynomial remainder computation. This is division with remainder. So you know what it costs, the evaluation at a single point is linear time, but we have to do it at n distinct points, because if the answer has size n, and we need n evaluation points in order to recover the value completely, but this is quadratic time, and you see that this is problematic. And for interpolation, you probably have been told that this is also quadratic time. So that's something that we will have to discuss next time, how to make this faster. So we will show, or we will first see that these complexities here are obtained before we had fast multiplication. But we will see that if we use fast multiplication just in these algorithms, as I said already in the beginning, then nothing will change in the complexity. I will show you why this is so. So we'll have to do something about it. And the goal will be to make it faster. Make it so fast that it's essentially linear. So this is quadratic. Quadratic is bad. We want to have it essentially linear. Well, let's keep this for last time and conclude here with this calculation. So you remember at the beginning I showed you this this computation where I asked Mathematica to solve this linear system, and you see it didn't give me the timing because it's still computing it. And I measured this when I prepared this lecture, and while I could wait for another 20 hours or so, I'm not going to make the video so long. I will stop this now, and I will show you an algorithm or an implementation of the algorithm that I discussed today. Yeah, so maybe I should make that a bit more precise here. I thought I had a slide for this, but I didn't. I said that in the end we said we go from kx to k, and then solve the problem there, and then we go back to kx. So that's hard, and that's easy, and that's what we will see next time is also easy, or at least efficient, and so we are happy. And for q we did the same. We said for q we don't want to solve the problem there. Instead we go to set p, solve it there, and then go back. Now what do you do, like in the example that I showed in Mathematica, where you have a linear system over qx. So here you have a problem over k, but k may still be complicated, like in this case. Then you do this twice. So with if the problem is in qx, then you first translate it. Now you have two options. Either you first translate it into q and then to set p, then solve it there, and go back to q, and then go back to qx. And the other possibility is you go, this is the one possibility. The other possibility is you go to set p of x. So you first take mod in the coefficients, and then you do evaluation with the x, then you solve the problem there, and then you go back in this way, set px, and from here to there. Now you can ask, what is more efficient? Which of these two choices? And the answer is the blue one is more efficient. And why is this? That's because, why don't we want to compute in Q? We don't want to compute in Q because computing in Q leads to a blow up of the size of the numbers. But evaluating x at a point is already a computation. So if you think of a polynomial here in qx, and you evaluate it at 5, or then maybe this is a polynomial of high degree, then you have to take 5 to a high power. This gives a long number, and then you have to multiply it with the coefficients and add things up. So this will be a high number, a long number. long number. And we don't like to compute with long numbers. On the contrary, if you go the blue way, you don't have this problem. You have a certain degree in x in these rational functions, but if you apply modular reduction to the coefficients to get from q to zp, then nothing changes about the x. It just stays what it is. The degrees don't get bigger when you take the coefficients mod p. So you don't have you have a blow up here, but you don't have a blow up here, and that's why this is better. And then once you are here, then the evaluation is harmless. So this one here is not as painful as this one here, because with this one you are in a finite field. So if you now take x and replace it by some element of the finite field, no problem. Even if it's a long number, it's just bounded. You can do the evaluation in such a way that everything keeps being bounded by p. So this one is nice, and this one is not so nice. So that's why you take the blue way. Okay, and this is what I programmed. So I programmed a linear system solver that takes a linear system over Qx and then plays this game and gives you a null space over Qx back. And let's just see how this works. Linear system solver, loading it. Sys x. Oh, sorry. Let me. So it takes a while. Okay, it surely doesn't take as long as the Mathematica thing, where I said it takes 20 hours, but it still takes a few seconds, so probably I should have started it before explaining what it does. Here it is. So this takes 20 seconds. So compare 20 seconds to 20 hours, and then you see the value of computing with homomorphic images. And also you see, I want to emphasize this, that the use of homomorphic images is a completely general method. It's not at all related to linear system solving. I've just chosen linear system solving here as an example problem. But you can use it for nearly any computational problem that you have with rationals, with rational numbers or rational functions. And in almost all cases, you will see a speed up when you use homomorphic images. So this is something which, unlike the algorithms that we discussed in the earlier part of the lecture, where you say, okay, here's the Schönhage-Strassel algorithm, it's interesting to know how this works, and it's maybe useful to know what it does, but as a user, you will probably not need to know how it works, but just how fast it is. And here it's different. For using homomorphic images, that's also something that you will be able to take advantage of as a user of computer algebra, and that's why I showed it today in such a great detail. So let's finally just check if the answer is right. I didn't check that before, so hopefully it is. So there is one solution. Let's see what it looks like. Okay, so this looks right. So sys applied to first of sol, then I get a mess of polynomials. I should expand it, and now I expect to get a list of zeros. So it is, okay. The approach I used here in this code is what in the slides I call the scenario 2. So I could compute a bound using Cramer's rule on how big the output is, but I'm not doing this. Instead, I go step by step because the bound, even though it's correct and it's also tight generically, But if you have meaningful input, then there is a good chance that your output is not as big as it could be in the worst case. And in the scenario 2, you will recognize this. You will go step by step, taking larger and larger. No, actually, you don't get larger and larger. You use Chinese remaindering, of course. So you take small primes and small polynomials, and then you merge them together. And whenever you have merged a few of them, you check, are you done? And if not, keep going a few more steps, and eventually you will see the result. Okay, so this is all for today. Next time we will discuss evaluation and interpolation from the perspective of efficiency, and I hope to see you again there. Thanks for watching.